So what we're going to be doing is talking about the vapor pressure of water. And if you remember, vapor pressure of water is something we introduced in the gas laws chapter when we were talking about partial pressures, and we talked about collected over water or CAL problems. In a collected over water problem, you had to look at the temperature, and you had to decide what the vapor pressure is, what by looking of water is by looking at a chart, and then we would correct the total pressure and subtract the vapor pressure to give us the pressure of the gas we collected. So vaporization is one aspect of that. Vaporization is the process of going from the liquid to the gas state. And this depends on several different factors. The first of which, being in this chapter, right, intermolecular forces. Now, vaporization happens at a rate, that is, a certain number of grams per second or milliliters per second. It happens at a rate. And that rate is dependent on the intermolecular force. If the intermolecular force is strong, then what happens is the rate of vaporization is slow. That slows the rate of vaporization down because the molecules, in order to get into the gas state, they have to have enough energy to escape from those intermolecular forces of the other molecules of the liquid. If it's weak on a relative scale, right, then the rate's going to be fast. So these are things, for example, that evaporate quickly. These have weak intermolecular forces and then high rates of vaporization. The other factor that's important to recognize is temperature. Now, this graph shows a little bit of what we're talking about when we talk about the effect of temperature on the rate of evaporation or vaporization. This is a distribution of kinetic energies, so how much energy the molecules have. So at any given temperature, for example, looking at the low temperature graph, there are molecules that have both low kinetic energy and high kinetic energy. This represents the fraction of the total number of molecules. So what happens is when you increase temperature, this curve begins to shift to the right. In other words, more molecules have higher kinetic energy and fewer molecules have lower kinetic energy. And as a result, the average kinetic energy of the molecules ends up going up. Now imagine that there's an imaginary threshold, right? And it's this dotted line. As the temperature increases, what happens is more molecules have enough kinetic energy to, if this represents the threshold needed to leave the liquid, right? More molecules will have enough energy to escape the liquid, provided that they happen to be at the surface of the liquid. Molecules on the inside might have that same kinetic energy, but they don't have access to the surface, so they can't escape into the gas phase. So temperature is one of the important factors, and if we're thinking about temperature, right, and rate, then what we're looking at is low temperatures would mean low rates. And that would represent the blue line here. And the low rate is a direct result of having fewer molecules with the minimum kinetic energy needed to escape the liquid. On the other hand, if temperature is high, then we expect the rate of vaporization to be high because there'll be more molecules with enough kinetic energy. Now, think about surface area, because surface area is an important aspect of evaporation rates. If there's very little surface area, okay, so let's say you have a bottle that looks like this, and you have liquid in it all the way up to here. Evaporation has to take place through that opening. And because it has to take place through that opening, only the liquid molecules that are here, right, can escape the liquid and become part of the gas phase. On the other hand, if you have an open container like this, and the liquid is like this, like the beaker shown over here, this is a larger surface area, And the larger surface area has more places for these molecules, if they're at the right energy, to escape, right? So when we're thinking surface area, right, if it's low surface area, it's going to be low rate. If it's going to be high surface area, it'll be a high rate. So let's think about one other case then, and this has to do with, let's say you had a little cube of liquid that looks like this, right? And it's in a little tiny container. The surface area that evaporates is that. And let's say this is 1 gram of water, right? So this would be 1 milliliter of water. If I take that same 1 gram of water and I get rid of the sides of the container, what happens to it, right? Think about what happens to this beaker when I get rid of the sides of the container. Well, what will happen, in principle, is the liquid would spread out like this. It's still the 1 gram of liquid, but what have I done to it by pouring it out like this? I've increased the surface area without increasing the mass. And this is something that you can do with the liquid. That is, basically, it's like a puddle, right? And you spread it out. And as you spread it out, you give it more surface area. So the surface area then will allow it to evaporate more quickly because there's more space for it to evaporate. Now, having said that, you know, like when you get sweaty, right? And what do you have this tendency to do? You spread it out. And what do you feel when you spread that sweat out, right? It cools you down. The reason it cools you down is because this process is endothermic. That is, it's absorbing energy as it spreads out. So this process, we see this effect all the time. So just give an example, right? You have a puddle of water on a desktop and you want to get rid of it. You don't have a paper towel. What do? You smear it out and then it evaporates very quickly. And then you can feel that cooling on your hand as it cools down, right? As it evaporates. A process, right? As this liquid is evaporating, these molecules in the gas phase are carrying the kinetic energy out and cooling the surface. Well, vaporization, when we're talking about vapor pressure, is in an equilibrium with the opposite process, which is condensation. And so what we need to look at next is the equilibrium between vaporization on one hand and condensation on the other. So let's talk about condensation. So let's discuss condensation. So condensation is this arrow that is going from the gas to the liquid state. And so the most common place that we can see condensation is on surfaces. And what happens is molecules with high kinetic energy can lose their kinetic energy when they collide with a cold surface. So when you take a shower and you're looking up, at the walls and you're looking at the windows and you see the fog on the window, that is a result of just the gas molecules leaving, right, the shower, and then hitting a cold surface and condensing on that surface. They could also collide with other molecules. And another place that we see condensation take place is on things like dust particles. So that's why when you form fog is actually small water droplets that form in the air. And they're, in fact, what they're doing is they're forming on particles of dust or like little bits of particulate in the air that allow them to lose their kinetic energy and go back into the liquid state. So the process is called condensation. It is exothermic. So if evaporation or vaporization is endothermic, then condensation has to be exothermic when it takes place. So let's talk about what happens when we're thinking about both evaporation and condensation. You have a container and you put some, let's say, water in it. Okay, so here's my water. And initially, none of it's evaporated. So I have zero um, gas phase, right? This is zero, but it's all in the liquid phase. And I'm going to put a lid over this. And then I'm just going to wait for the liquid to begin to evaporate. So it evaporates, right? And I start to get gas in water molecules in the gas state, filling up the container. And once that reaches or once this starts increasing, then what can happen is these molecules can begin condensing. So initially I have a rate of vaporization. It's determined by the temperature of the water and surface area. And the intermolecular force. I should put all three. Those are what determine the rate of vaporization. But as long as the surface area doesn't change, right, and the temperature doesn't change, so we assume it's a constant temperature, then the rate of vaporization will be constant. So what we're showing here is this is time, right? This is rate. And this is the rate of evaporation or rate of vaporization. It's a constant value going across. However, as the concentration of the gas particles, the water molecules in the vapor state increases, then what happens is they can begin to condense and form like liquid layers on the surface or go back into the liquid here. And so the rate of condensation increases as the concentration of water vapor increases. Eventually, these two things will reach an equilibrium. That is, the rate of evaporation and the rate of condensation are the same. What does it look like in here? It looks like the concentrations of the gas molecules stops changing. And this is what we refer to as the vapor pressure of water. So this vapor pressure is measured under the conditions at which evaporation and condensation are equal to each other. Now, what happens if you increase the temperature? Well, if you're at equilibrium right here, right, and you increase the temperature, then you're going to increase the rate of evaporation, so the line will move up. And then what will consequently happen is the rate of condensation will begin to go up until, again, it meets the rate of evaporation, and then you establish a new equilibrium. Now, the thing is that at that new equilibrium, because you've got more gas molecules in the gas phase, your vapor pressure will be higher. So vapor pressure of a liquid goes up as the temperature goes up. But at all times, we're always measuring under the conditions of dynamic equilibrium. So here's an interesting thing about the vapor pressure of a liquid. You can disturb the equilibrium by changing the volume above the container. So imagine that this is the situation that you have. You have a dynamic equilibrium taking place where the rates are the same, right? Now, the rate of condensation is related to the concentration of the molecules above the liquid. So what happens when you increase the volume? Increasing volume means lower concentration. But you don't affect the rate of evaporation. And so what ends up happening is the system's at equilibrium here. Now all of a sudden it's out of equilibrium because you've lowered the concentration of the gas molecules. Eventually, though, what ends up happening is because the rate of evaporation is constant and the rate of condensation is lower, eventually it will reestablish equilibrium and you'll come back to the same pressure that you had over here, just in a larger volume. Now, if you do the opposite, right, if you squeeze this down, then what ends up happening is the rate of condensation will go up because this means higher concentration of gas. And so what ends up happening then is the rate of condensation is greater, right, than the rate of vaporization. So filling in these sentences, vaporization rate is larger than condensation rate. And then the vaporization rate is smaller than the condensation rate. But the thing to remember, though, that's happening is it's not the rate of vaporization that's changing to make that happen. It's the rate of condensation that happens. Eventually, though, all three of these systems, regardless of how much space is above the liquid, reach the same vapor pressure for water, or this, whatever this is, looks like it's octane or something, whatever this molecule is in here, that vapor pressure in this container, and this container, provided you wait for it to come back to equilibrium, will all be the same.